Hello, my name is Professor Shaun from the University of East Anglia, and welcome to this short video about mathematical proofs. So there are a few things that I'd like to talk to you about today. The first is what are proofs? Then why do we need to bother with proving things? And finally, and maybe the most important thing for taking away, is how should we actually be writing proofs? So I'm going to start off with what are proofs, and I want to start by telling you a story. One of the most famous results in mathematics that took a long time to be proved is something called Fermat's last theorem, which you may have heard of before. So the story of Fermat's last theorem begins a long time ago, and perhaps we could start with a mathematician called Diophantus. So he lived in the 3rd century of the Common Era in Alexandria, but we actually know very little about his life. But what he's famous for is having written a large text called the Arithmetica. Not all of it survives today, but it was very influential. And so Arithmetica meant it was about arithmetic, which to him meant solving problems or solving equations where the solutions were supposed to be whole numbers, so integers, or sometimes rational numbers. So he wouldn't have expressed them as equations the way we think of it now with algebra, but that was what he was doing. Okay, and so as I said, his books, the Arithmetica, were very influential and were translated into other languages and eventually made their way a long time later to our next character, who is Pierre de Fermat. So Pierre de Fermat was actually a lawyer. He wasn't a mathematician at all, though he was, he's not a professional mathematician. But he was a very good amateur mathematician. I mean, one of the best of his time. And in particular, he really almost invented what is now called number theory. He was especially known for setting mathematical challenges. So he would write in letters to other mathematicians saying he could do such and such a thing, and could they? But interestingly, he actually never published any proofs. So although he set challenges, and this is about proofs, he was not a great one for proofs. So what was this thing called his last theorem? So this came about, in fact, really after his death. So his son published another edition of this book, Arithmetica, by Diophantus, and this is an extract from a reprinting of it, in which he included some commentary that his father had made, and this is this here, where it says, this is in Latin, it says the observations of the father Pierre de Fermat. And so what's this all about? So in modern language, this was problem 8 here. And what it talks about is finding integer solutions to this equation. X squared plus y squared equals z squared, which I'm sure is an equation that you recognize from things like Pythagoras' theorem, where x, y, and z could be the 3 sides of a right-angled triangle with z the hypotenuse. And then we would know that x squared plus y squared is z squared. And so there are solutions like 3, 4, 5, because we know that if we have we can have a triangle where the side lengths are 3, 4, and 5. And this works because 3 squared plus 4 squared is 9 plus 16, which is 25, which is 5 squared. So this is what this question was about. And so what was it that Fermat wrote? Well, so this is a translation. It says, it's impossible to separate a cube into 2 cubes, or a 4th power into 2 4th powers, or in general any power higher than the second into two like powers. And really, maybe the more significant bit is, I have discovered a truly marvellous proof of this, which this margin is too narrow to contain. And this is the thing which made this problem famous somehow. So, the problem, as you can see, was written in words, so let's write it in algebra the way we might recognize it. So rather like the x squared plus y squared is z squared. So what is it saying? It's saying that if instead I look at a bigger power, so I have a power where I have, say, 3 would be cubes, or 4 would be fourth powers, but I have any power which is at least 3, and I try to solve the same sort of equation, but now the power is n, well, I can't find any. There are no non-zero integer solutions to this. And he claimed he had this marvellous proof, but the margin was too small to contain it. So, what happened then? Well, people tried to prove it. And so this was in 1637 is when he stated it. So the book was published, he stated it then, but the book, the edition, as I showed you, was published in 1670. But still, he stated this in 1637 and moved forwards 358 years. And Andrew Wiles, who's a British mathematician, finally in 1995, he put in place the final piece of the puzzle which completed the proof. And when I say the final piece of the puzzle, I should point out that's not just like a little piece. Already just his little piece was about 200 pages of mathematics. And it built on a huge amount of mathematics which had happened over the previous 350 years. Due to lots of famous mathematicians like Euler and Gauss and so on, whose names which you may have heard of. I'm not going to talk about any of them today, and I'm also not going to talk about the proof of this theorem because it is very difficult. But it's just to illustrate that proofs are something which motivate a lot of mathematics. So, why do we need to have proofs at all? If Fermat said there are no integer solutions to this, and if we look a bit and we can't find any, well, maybe we should just be happy. And that's it. Okay, so here are a couple of examples to show why we might want to do this. So there's a thing called the strong law of small numbers. It's not a very official law. It was suggested by a mathematician called Richard Guy in the 1980s. And one way of saying it is there are not enough small numbers. So here's a first problem. And it's a problem which you might want to try. So here's what we do. We take a circle and we put n points around the circumference. So we could say we got put 3 points. And we're going to draw a straight line between every pair of points. Something like this. And it splits the circle up into different regions. And what's the maximum number of regions possible for a fixed number of points? So for example, with 3 points, we can see we've got 1, 2, 3, 4 regions. But maybe if we put more points, we'll get more regions and so on. And the question is, for each number, what's the most that we can get? So let's try a few here. So let's start off with 1 point here. How many regions have I got? Well, there are no lines I can draw, so I've just got one region. That was nice and easy. Okay, so now suppose I have myself a second point somewhere over here, and now I draw a straight line joining them. How many regions have I got? Well, I've got 2 now. And what you could perhaps do is just pause the video now and keep filling up this table and make a guess as to what should go down here for how many there are when there are n points. So hopefully you've had a go. Let me keep doing some more anyway. So we could have a third point here, which we would join up, and we have already seen, in fact, that there are 4 regions, and this is looking interesting because these look like these are powers of 2. So let's try putting in another point, and we get 3 more straight lines. And how many regions have we got now? So let's count them up. We've got 1, 2, 3, 4, 5, 6, 7, 8. 8 regions. And we might notice, well, this one is 2 cubed, this one is 2 squared, this one is 2 to the power 1, this one's 2 to the power 0. So perhaps this should be 2 to the n minus 1. And it really looks like it is, doesn't it? Sadly, it turns out that it's wrong. So I will leave you the challenge of working out how quickly it goes wrong. It actually doesn't take much longer, but this is wrong. So it looks like we've got this nice pattern, but we don't. Okay, so this one, we don't actually have to go that far before it starts going wrong. Here's another one though. So if we think about prime numbers, and whenever you have an odd prime number, if you divide it by 4, the remainder is always either 1 or 3. So for example, if I do 5 divided by 4, this leaves a remainder 1. But if I do, I don't know, 23 divided by 4, so 4's going 5 times, that's 20. So this leaves a remainder of 3. Okay, so we always either leave a remainder 1 or a remainder 3. And what we can do is we can have a race. We can say, well, let's list the odd prime numbers according to the remainder, and which remainder is going to win the race. So we're going to put the numbers into these 2 columns according to what the remainder is, and we're going to see what happens. So here they go. So the first odd prime number is 3, so that has remainder 3. Then we have 5, which has remainder 1. And then we have 7, which has remainder 3. And then we have 11, which has remainder 3 as well. So the remainder 3 is getting ahead a bit now. And we keep going. And 13, oh, 17, the remainder ones have caught up. Oh, but remainder 3 goes ahead again. Remainder 3 is well ahead at the moment. Oh, remainder 1's caught up, but remainder 3 goes ahead again. Oh, it's well ahead. Remainder 1 looks like it's catching up. No, remainder 3's ahead. Oh, it's still ahead. And so I'm going to stop there. And certainly what we've seen so far is that remainder 3 is staying ahead all the time. It's always at least as far as there are at least as many prime numbers in that column as there are in the other. Okay, so I would suggest you pause the video, maybe try writing a few more, check to see whether the same thing still seems to be happening. And if you've done that, then unless you got yourself a computer to start checking things, you will have found that the remainder 3 is always ahead. So you might think it'll always be ahead, but it's not. Okay, so the first time remainder 1 goes into the lead is at the number 26,861. So you have to go quite a long way before remainder 1 goes ahead. And even then, it just slips ahead and then remainder 3 catches up and stays ahead for quite a lot longer again. So the point is, the things which they look like they're true, perhaps they're not really. So that's why we need to prove things. And so this is one example where the number is quite big. There are other examples in mathematics where there are things which look like they're true, and the first time they go wrong, you're talking about numbers with hundreds of digits. Really enormous numbers. So that's why we need to prove things. So now we know we need to prove things, so what actually is a proof? So again, if you're with a group of people, or even if you're on your own, you might want to just pause the video, have a little think about what you think, have a discussion about it, and then start again. So this is a rather beautiful proof of Pythagoras' theorem, which I want to show you, because if you know Pythagoras' theorem and you know what this is saying, then you can see how lovely this is. Okay, so this is a geometric proof of Pythagoras' theorem, which shows that when you have these yellow right-angled triangles, here we have the blue square, which is the square on the hypotenuse, and the 4 triangles, and I rearrange them, and I end up with the 4 triangles still, but now 2 smaller squares, which are the 2 squares on the other 2 sides. And so the blue square, the area of the blue square, must be the same as the area of the 2 green squares. Now, a lot of people, once you understand Pythagoras' theorem, will say that this is a really wonderful proof. These are called proofs without words. So I would say that that's only useful once you already understand, once you already know a proof, or if you've got somebody there to explain it to you. So it's really important that a proof is explaining what's going on. And so I think that what you really need in proofs are you really need words when you're first seeing things. So what would I say a proof is? Okay, so a proof is meant to be an explanation which shows with 100% certainty that a mathematical statement is correct. So this is not like proof in a court of law where you want to do something beyond reasonable doubt. So you want to be almost certain or something like that, because otherwise all those things that we saw before which seem to be right to begin with, you would say, oh, that's almost certainly true, and you'd be wrong. The purpose of writing a proof is to communicate. So you need to communicate the explanation of the proof. So it's not just about you showing that about you saying, I understand this. It's about you showing that to other people and explaining it to them. One of the problems with this is that how much detail do you need to give? And that really depends on who your reader is and what they expect of you, and arguably what you expect of them. So, for example, if you're going to be writing a proof of something, you're not going to be expecting to have to explain to the reader what algebra is and manipulating equations. You expect that they know that already, and that wouldn't be reasonable for you to be doing that. On the other hand, what manipulations you're doing, that's a thing that you would want to explain. You'll probably have noticed also that there was this little asterisk here. So proofs are supposed to be things with 100% certainty. The problem is that proofs are done by humans, and humans make mistakes. And so there are examples of things which people thought had been proved, and then later it was found that there was a mistake. And that's maybe a different story for another day. But the idea is that you should be absolutely certain. Okay, so what we're going to do in the rest of the videos, I'm going to show you an example of a proof of something that you know. So I expect you've seen the cosine rule before. So the cosine rule is actually just a generalization of Pythagoras' theorem. So here it is. Suppose a triangle has edge lengths A, B, and C, and that the angle opposite to A is theta, then a squared plus b squared plus c, a squared is equal to b squared plus c squared minus 2bc cos theta. And here's a picture to go with it. So for example, if theta here happened to be a right angle, then cos theta would be 0, and so this term is not here, and so you just get Pythagoras there. So what you're going to find on the next slide is a student's proof of this in the case where the angle theta is obtuse. And this is a proof where already they know Pythagoras' theorem, so they can use that as part of the proof. And they know trigonometry. So here it is. This is actually taken from a wonderful book by Kevin Houston called How to Think Like a Mathematician. And if you're looking for things to prepare you for university, that's a wonderful book to look at. So what I suggest you do now is just have a look at this and pause the video and have a think about what's good and what's not good about this proof. Okay, so hopefully you've had a little think. So what things do I notice when I see this proof? Okay, so the most striking thing, I would say, there are no words. So if this is supposed to be an explanation, that's going to be jolly difficult to read without words. And it's kind of a shame because actually everything that's needed here is here. So all the steps in the proof are actually here. They're just laid out in a way that makes it rather difficult to read unless you already know what's supposed to be happening. So, for example, suppose I read it as you would normally read. Okay, you read from left to right, so I have a nice picture. And then it says, triangle CBL, triangle CLA, a squared equals c plus x squared plus h squared, b squared equals h squared plus x squared. So that's not really very helpful. I mean, what's really going on is that we've got two separate blocks. We've got a block here, and we've got another block here. And then we have this unfortunate thing with an arrow where, well, I'm supposed to guess what's going on there. I mean, I can guess, but then I have experience, so I know what I'm supposed to be guessing. Similarly, at the end here, right? So we've got another arrow which is telling us where to go back to, and it would have been much better not to have that. One thing which is maybe a little bit subtler, which you may not have picked up on, is this. Okay, so what's the problem with this? So the problem with this for me is that equals sign. This says theta equals obtuse angle. And that's not what the writer means. What the writer means is theta is an obtuse angle. That's not saying it's equal. So equals is two things that will be equal when they're absolutely identical. Okay, so like two numbers which are the same number, for example, would be equal. But obtuse angle is describing a property that something has. And that's not what theta is. Theta is an angle. So it's important to use symbols correctly. Symbols are very useful, but you need to be used correctly. So let's summarize some of these. So write in sentences. It's the first and most important thing. Keep the reader informed of what you're doing. Okay, so at every step, make sure you explain what you're doing. And if you make an assertion, explain where it came from. So something which I didn't mention, but here, they just wrote down b squared equals h squared plus x squared. How did they know that? Okay, so you know how, and I know how, but they should have written down why. So equal signs mean equal signs, and like I said, don't use arrows. If you're having to use arrows, that means you've written things down in the wrong order. And so, again, this, for me, is a really, really good rough working proof. So this looks to me like rough work. And having written that down, and now you know how to prove it, and you know what order you should have put things in because you've got arrows here, so you know what should have come before what, then we can actually write down a proof. So what I'm going to do now is talk you through how I would write down this proof. So here is the picture. It's essentially the same picture that we had. So here's where I would start. I would start actually with where the previous proof finished. So looking in triangle CLA, we have cos of 180 minus theta is x over b. So I'm assuming that my reader knows trigonometry, so I don't need to write down that cos is adjacent over hypotenuse. I'm also assuming that they know a bit of geometry, so that angles on a straight line add up to 180, so that this angle is 180 minus theta. And at your level, that's fine, I think, to assume that. Okay, so then we say, so since cos of 180 minus theta is minus cos theta, this rearranges to x is equal to minus b cos theta. And I know this is going to be useful later, and so I give it a name. So I've called it star. You can call them 1 or 2, or whatever, however you want to label them. But I have a label to be able to refer to it later. Then, since the triangle is right-angled, Pythagoras' theorem says b squared is x squared plus h squared. Okay, so this is this right-angled triangle here. And again, I've labelled it for use later. And then I say, well, since my big triangle, CLB, is also right-angled, Pythagoras' theorem says, and I write down what it says, that the hypotenuse a squared is c plus x squared plus h squared. Okay, so now I've run out of space on the page. So here, this is where we got to. We got down to this line. And now I can just start multiplying this out, expanding out, and substituting. So first of all, I say, I expand out my brackets, and I've written by expanding. Then I say, oh, I can substitute for x. So by substituting from star, which was x is minus b cos theta up here, I've just substituted in. Then at the next stage, well, I've actually done two things, but I think the first one is just some basic algebra of rearranging, so I think doesn't need any explanation. But I have also substituted from dagger. Okay, the x squared plus h squared, I've substituted for b squared. And now you see, what have we got? We've got something which says that a squared is equal to, and eventually is equal to, what we wanted. So finally, all we need to do is write down the conclusion. Thus we have a squared is b squared plus c squared minus 2bc cos theta as required. And you can see there are a lot of words there. And this is really, when you're writing down proofs, this is what you should be looking to do. Really explain with words. Okay, so that's it for today. I'm going to leave you with something to think about, to take away. So you will all know that there are infinitely many prime numbers. So here is a proof, maybe. So this result was actually originally the first place that we know of it being stated formally is in the work of a Greek mathematician called Euclid from about the 3rd century before Christ, and his proof is in some ways not dissimilar to this one, though a bit better. But anyway. Here it is, PQR primes, PQR plus 1 has a prime factor which can't be PQR, so there's another prime. Now repeat to get infinite primes. Okay, so that's short and sweet. So what I want you to take away and think about, and again discuss, what are the problems with this? Can you write it out better? And have a go. And have a go, and don't be satisfied the first time you do it. Write it out and then think, could I have done it better? And in doing so, are you making any assumptions? So are there things that you're assuming that people know already? And if so, was that reasonable to assume? If you have heard of it, then you may want to, so with writing it better, you may want to think about a thing called proof by contradiction. If you've not heard of it, we'll talk about it in the session. And there are also other techniques for proof, which I hope we'll get to talk about. Okay, so that's it for this video, and I hope to see you in the session.